In 1802, a French mining engineer proposed tunneling beneath the English Channel to permanently connect Britain and France. The British government refused, so did every government after, for nearly 200 years. The Channel Tunnel would eventually become one of the most ambitious engineering triumphs of the 20th century. But the story of how it got built starts with why, for so long, it didn't. Albert Mathieu Favier's 1802 design featured a double-decked passage illuminated by oil lamps, where horse-drawn coaches would stop at an artificial island on the Varne sandbank. While British defense anxieties immediately shelved the plan, scientific curiosity persisted. By 1839, French surveyor Aimé Thome de Gaumont began taking physical soundings, eventually proving a continuous layer of stable chalk marl spanned the seabed. This geological discovery prompted the British Parliament to pass the 1875 Act, authorizing initial test shafts. Though the English trials at St. Margaret's Bay flooded, French crews at Sangatte successfully sank a shaft to 330 feet. By 1882, engineers utilized Colonel Frederick Beaumont's compressed air boring machine to cut thousands of feet of pilot tunnel under the channel, before British military concerns once again halted progress. Interwar proposals in the 1930s quickly faltered under the weight of the Great Depression and lingering strategic doubts. Decades passed before both nations established a new approach. In October 1973, British Environment Secretary Geoffrey Rippon presented a government white paper granting renewed approval for a state-backed fixed link. Work began, but the momentum was short-lived. By January 1975, facing soaring projected costs, the global oil crisis, and severe pressure on British public spending, the British government unilaterally abandoned the project. This sudden cancellation exposed the divide between technical capability and political permission. Yet the idea persisted. In 1984, both nations revived the proposal, shifting the concept from a state-funded venture to a privately financed enterprise. After a century of false starts, the fundamental question remained: what would turn this political ambition into a physical reality? Translating this private enterprise into a physical connection required prioritizing geology over geography. Engineers could not simply choose the shortest path across the Strait of Dover. Instead, they mapped the route to follow a continuous rock layer beneath the seabed known as the chalk marl. Located below water-bearing upper chalk and above dense gault clay, this clay-rich stratum offered a stable and virtually waterproof shield. Because the dry chalk marl could support its own weight during excavation, it allowed engineers to plan a controlled bore without the immediate risk of cave-ins. Keeping the tunnel within this protective layer meant following a precise, undulating profile rather than a straight line. The final route spanned 21 kilometers across the strait, dropping at its deepest point to 75 meters below sea level and 115 meters below the muddy seabed. This placement kept the work safely insulated from the massive volume of water overhead. At 75 meters below the sea, the weight of the English Channel exerts a hydrostatic pressure of 7 bar, transforming any rock fracture into a potential pathway for a catastrophic flood. To mitigate this hazard, British and French engineers adopted distinct tunneling strategies suited to their respective geologies. British crews, working in the drier, more stable chalk marl, utilized open-face, shielded tunnel boring machines. Conversely, the French team faced highly fractured ground, requiring closed earth pressure balance machines that maintained controlled face pressure to hold back the water. The plan dictated a 3-tunnel layout: 2 outer running tunnels for rail traffic and a smaller central service tunnel for maintenance and emergency escape. As the machines excavated, crews immediately lined the walls with interlocking precast concrete segment rings to support the immense overhead load. To ensure these separate paths met precisely in the middle, surveying teams on both coasts established a shared geodetic reference network, guiding the machines using lasers and gyrotheodolites. Underground, crews worked in 3 continuous shifts, drawing experienced labor from British mining towns and the industrial centers of northern France. This complex technical system began operation in 1988. In 1985, a public-private competition shifted the fixed link project from a government ambition into a privately funded mega-project. The 1986 concession went to Eurotunnel and the Transmanche Link Construction Consortium. Led by Sir Rod Cox, this private finance model placed all cost and schedule risks on the concessionaire and its lenders, operating entirely without public subsidies. The initial plan targeted a 1993 opening, with construction costs estimated at £4.8 billion. By the time of financial closure, this estimate surged to £9.5 billion. When main excavation began in 1988, the project transitioned from experimental pilot trials to a continuous 24-hour industrial operation. This unforgiving scale soon exposed severe mechanical and physical strains. On the French side, highly fractured ground caused rapid cutter head wear, demanding constant maintenance and extra equipment. Worse, a sudden water inflow of 3,000 cubic meters per hour halted the French tunnel boring machines, requiring extensive grouting, additional waterproofing, and costly safety modifications. As physical progress slowed, financial pressures mounted. Rising interest rates inflated the debt service of a syndicated loan facility backed by 180 international banks. By the late construction phase, the project ran £2 billion over budget, pushing the consortium to the brink of insolvency. To prevent a complete halt, Eurotunnel negotiated a massive restructuring, securing additional shareholder equity, extending repayment terms, and revising loan conditions. This complex web of debt and engineering became a grueling test of endurance, where progress had to be sustained before political and financial confidence ran out. On the 1st of December 1990, workers Graham Fagg and Philippe Cosette broke through the final rock partition 40 meters beneath the English Channel. Their meeting joined the service tunnel headings, physically linking the British and French sectors for the first time. The alignment of the boring machines proved the accuracy of the coordinated coastal measurements, with the two sides converging within centimeters of their calculated targets. This breakthrough established a continuous 30-kilometer undersea service route for ventilation, drainage utilities, and emergency access, validating the separate national excavation efforts as a single coordinated line. Yet this physical connection did not represent an operational railway. While the crews exchanged greetings of Hello France and Bonjour England, the two larger passenger tunnels remained unfinished, with years of track laying, electrical fit-out, and safety testing ahead. Excavation of the remaining railway bores concluded in 1991. The northern running tunnel broke through in May, and the southern tunnel met in June, completing the physical undersea geometry. Between 1992 and 1993, crews transformed these empty concrete tubes into a functioning railway. Workers laid 30 kilometers of continuous welded track, hung overhead power lines, and installed the TVM 430 in-cab signaling system. Massive ventilation plants were built to circulate 3 million cubic meters of air per hour, alongside fire suppression systems designed to secure the 50-kilometer passage. System testing began immediately and intensified after the formal handover to Eurotunnel on December 10, 1993. While original plans allocated 6 months for commissioning, the integration of complex rolling stock and safety protocols extended this phase to a full year. Priority was given to freight shuttles, which began moving commercial goods in early May 1994. On May 6, 1994, Queen Elizabeth II and President François Mitterrand officially opened the link. This ceremony converted the active construction site into a working cross-channel transit corridor. Today, the 35-minute rail crossing between Folkestone and Calais supports Eurostar passenger trains, freight operations, and vehicle shuttles. By 2022, annual traffic reached 23 million passengers, demonstrating how a route managed by fixed infrastructure replaced reliance on maritime and air crossings. The completed project stands as a practical example of sustained international coordination. The tunnel altered travel between Great Britain and continental Europe without erasing national boundaries or solving every regional transport problem. Instead, it remains a highly engineered operational link within a broader European transport network. Today, the Channel Tunnel is a permanent physical bond. While political landscapes shift, this undersea route endures, proving that while borders can be redrawn, the concrete and steel of shared engineering remain unyielding. Subscribe for more deep dives into engineering history.